start with the cold. So we're going to do acute, chronic, and illnesses, just like we did with heat and just like we will do with altitude. So really there's two main things that we're going to get through with this lecture. Just basically what happens when you go into the cold. Now, one of the responses that happens in the heat, the response is essentially opposite in the cold. So if we're in the heat, what happens is we vasodilate, blood flows through the skin blood vessels, and we lose heat. We don't want that in the cold, and so what happens is we have this vasoconstriction, and so blood is preferentially diverted to places that are below subcutaneous fat, and so now we have those same blood vessels, and the blood that's carrying the heat, but the heat can't escape because the fat acts as an insulating layer. And so, just to kind of put this in words, when we have low core temperature, and that's the important thing, is that it's got to be a low core temperature, this causes our skin blood vessels to vasodilate, ultimately decreasing skin blood flow. Okay, but it's like it says here, this doesn't happen just in the skin, it happens to all peripheral tissues. So hands, arms, feet, legs. We can't do this, or we don't have a similar response in our head because the blood vessels in our scalp have no vasomotor control. And so what that means is they don't really constrict or dilate. All right, and this results in a redistribution of blood flow. And so if the blood isn't in the periphery, where does it end up at? Well, it ends up in the core. And so as a result, we have an increase in central blood volume. Now, from a physiological standpoint, this is good because it increases core temperature, helps us to maintain core temperature, but there are some other consequences that occur as a result. So ultimately, because we have greater central blood volume, that means we've got greater stroke volume. If we have greater stroke volume, we're going to have changes in pressure. And just if the only thing that changes is an increase in stroke volume, then blood pressure will go up. And so we want blood pressure to go down. And the way we do this is we urinate more. Okay, and so if you've got a balloon and it's got lots of pressure inside the balloon, well, what can you do? You can get rid of the fluid or the air that's in the balloon. And so you do the same thing, or we do the same thing. And so we increase our urine volume, and this is called cold-induced diuresis, which will help reduce blood pressure. So if we take this back to the Fick equation, remember Vo2 max, and actually it should say VO2 here. So VO2 equals cardiac output times the AVO2 difference. And so VO2 equals heart rate times stroke volume times the difference in content. If we went one step further, VO2 max would equal heart rate max times stroke volume max times the max difference between arterial and venous content. So if we want to understand changes to VO2 max, well, we need to understand what happens to each of these variables in the cold. And so, again, I mentioned this or alluded to this a minute ago. In order for the cold to really have any effect, well, core temperature must be lower than normal. If core temperature is not lower than normal, there's not going to be any direct effect of the cold on VO2 max. Okay? So, if we've got cold or a low core temperature, max heart rate likely decreases, and so what we do is we increase our stroke volume. And this results in a decreased maximum cardiac output. Okay. Another thing that happens is that hemoglobin binds to oxygen more tightly at low temperatures. Remember, we get that left shift of the oxyhemoglobin curve, and so oxygen will stay, or it's easier for oxygen to load and stay on a red blood cell. As a result, due to both of these things, we have reduced delivery. Okay, so due to the fact that maximum cardiac output is decreased and the fact that oxygen wants to stay with hemoglobin, we're not able to get as much oxygen to the muscle as necessary. Another thing that also makes this difficult is if we're constricting the periphery, which is where your legs and your arms are, that could result in decreased blood flow to your skeletal muscle. This would also reduce oxygen delivery. So what happens in the cold? Okay, so like we said, we need core temperature to drop. If we have a little bit of cooling of muscle, fatigue actually occurs at a slower rate. All right, so we're just talking slight fatigue. However, if we get our muscles very cold, so below 27 degrees Celsius, then we lose muscular endurance. And there's a few reasons why this might occur. It's not fully understood, but we know that the speed with which action potentials travel is reduced. It might be more difficult to recruit muscle fibers. And it might also just be more difficult for muscles to go through cross-bridge cycling, which we'll talk about in a few minutes. Okay, and so to give you a better idea of how endurance performance in the cold is affected, we have this figure here. And this is from an important paper that was done by guys named Galloway and Mon back 25 years ago, almost 25 years ago, which is kind of nuts. Okay, and so on the x-axis, we have ambient temperature in degrees Celsius. On the y-axis, we have time to exhaustion. Okay, and so what happened was they had several people get on a bike, cycle at 70% of their Vo2 Max, I believe it was, and they just went until they couldn't go anymore. Okay, and so notice that the best temperature based on this study appears to be around 11 degrees Celsius, which is just above 50 degrees. And so we've kind of got this reverse parabola shape, something like that. So as we go away from 11 degrees, whether hotter or cooler, endurance performance decreases. Now, obviously, there's going to be different mechanisms to cause this decrease in performance, but it does happen. So 50 degrees seems to be good for aerobic performance, right? And so I love it in the mornings, and part of it might be the fact that I've read this study, but I love it when I go for a run in the morning or whatever, and it's about 50 degrees outside. That's perfect running weather. Now, if I were to ask a sprinter about that, they would probably have completely different opinions, which we'll get to here in just a minute. So, well, what's going on? So in the cold, we have a higher VO2 at a given workload. And the reason that this might occur is that there might be greater muscle tension in each of those muscles. And so we have to overcome this tension, which requires more oxygen. And so VO2 is going to be higher. Okay, this happens because skin thermoreceptors, when they're activated, increase that muscle tension and or muscle metabolism. So if we increase muscle metabolism, that's also going to require more oxygen. Okay, so if you think about it, in the cold, well, what do you do when it's in the cold, right? So if I offered any of you, I said, hey, I will give you an A in this class, guaranteed, no matter what. And let's say I did this at the beginning of the semester. You don't need to come to class. You don't need to go to the lab. You don't need to do any of that. You just have to do this one thing. I need you to go run a 5K when it's 25 below outside. Well, what are you going to do? Okay, if you agree to this, you're not going to just get out, in your normal running clothes, shirt and shorts and shoes. You're probably going to look like that little kid in A Christmas Story that can barely move. You're going to be fully clothed, lots of layers, bulky. It's going to be hard to move. Doing this to maintain your core temperature is going to increase your VO2 as well because, well, one, the clothing adds weight, all right? And then when you sweat, that adds weight to the clothes. And then the other thing is that you're not going to be able to move very efficiently, right? You're going to have poor economy of effort because the clothes are going to hobble, okay? And then you're going to actually increase friction. With more layers, there becomes more drag, and that will also require more energy and effort to overcome. We can also increase VO2 for a given intensity if we're shivering. Okay, so this figure here, we've got on the x-axis, we've got intensity. On the y-axis, we've got VO2. So we've got the orange is just neutral, ambient air, regular temperature, however you want to think about it. Blue is in the cold, and also think about it in terms of if we're shivering. Okay, in order for our muscles to shiver, okay, which are those involuntary contractions that we've all experienced, we're probably experiencing them today since it snowed last night, that requires oxygen. And so as a result, we're going to hit max cardiac output earlier, and we're not going to be able to exercise for as long. Generally speaking, shivering occurs when your core temperature drops to about 35.5 degrees Celsius, although there is quite a bit of variability. All right, so how does cold affect muscle function directly? Well, as we said a minute ago, the nervous system is affected, and if I mess up with, or if I alter the nervous system, that's going to alter the muscular system. And so we're not going to be able to recruit our muscles or our motor units as effectively. It's going to be more difficult for the muscle to shorten, to go through cross-bridge cycling, so you have a power decrease. All right. as we said earlier, it's really not until muscle temperature gets pretty cold before we start to see these effects. So if your muscles are warm enough, then power production isn't affected. All right, but where this can play a role is if you get tired, right? So if you increase fatigue, you start working at a lower intensity, which means you're producing less heat, which means that your core temperature is going to decrease at a more rapid rate. This leads to fatigue, which leads to even more intense, a greater decrease in intensity, so on and so forth. This is a positive feedback loop here. Okay, and so it can be challenging exercising in the cold, especially as you get tired. So resistance training, we talked about this a couple of weeks ago. So other things that can decrease or alter muscular endurance, power, and strength is that decreased conduction velocity. We're not able to recruit as many fibers. It takes longer for a muscle fiber to get to its maximal force production. We have decreased cross-bridge cycling. Chemical reactions slow down. The sarcoplasm viscosity increases. Okay, so it becomes thicker, more dense. Okay, think if you've ever cooked and you've got an egg that's been sitting in the fridge as opposed to egg that's been sitting on your counter, and you break both of those eggs open, there is a difference in the egg white. Okay, the egg white that's been sitting out on the counter is going to be less viscous or kind of more runny, whereas the one that you just pulled out of the fridge is going to be thicker, more viscous. Okay, so if it's cold and you're doing something powerful, sprinting, jumping, that sort of thing, you're going to lose about 4 to 5% of performance for every degree Celsius that you drop in muscle temperature. Why? Cross bridges. It comes back to cross bridges, right? So we're not going to be able to have that cross bridge cycling occur as quickly. This viscosity will also increase resistance, right? Runny versus not so runny. And then we'll also have decreased chemical reactions. So endurance training, not a big deal, or endurance activities, not affected quite the same degree. But when it gets to those high explosive, high power, high intensity exercises, the cold plays a huge role, right? And if we had sprinters in class or people that did those very explosive activities, one of the things that they don't like about the cold is that there's an increased probability that they can hurt a muscle because of these factors that we've got mentioned here.